Hey folks, welcome back. So this is another video about data analysis, and it follows on from a series of videos I've just been recording about ANOVA, analysis of variance models, where we've worked our way up from one-way ANOVA to factorial ANOVAs, independent groups, repeated measures, mixed designs, things like that. And along the way, I've kind of covered some tests of assumptions for ANOVA models, some statistical tests that can be used for tests for assumptions. And I've discussed kind of like the value of them, whether they're a good thing, whether they work well or not. But I've only really covered assumptions in a kind of ad hoc way. So I thought I would finish off this kind of series on ANOVA by with just a little bit more detail about tests of assumption for ANOVA models. So a number of assumptions about the data have to be met when using ANOVA statistical models for these type of inferential tests. And I've covered these to varying degrees in other notebooks, in other videos, where I've analysed data using ANOVA. And what I'm going to do in this particular video, I'll cover a number of tests that are supposedly necessary tests of assumptions for ANOVA. I'll go into them in a bit more detail. I'll show you how assumptions can be checked in various ways using different software packages in Python. So the three key assumptions that we need to meet for data to be analysed by fitting an ANOVA parametric statistical model are assumptions about independence of data points. And this is the assumption that observations in each group are independent of each other, and that observations within groups were randomly sampled from the population. Assumptions about normality, and this is that scores in the sample were drawn from a normally distributed population, and also certainly for independent groups designs, homogeneity of variance. So the variances for the population that each sample group is drawn from are equal. Okay, so I'm not going to talk about sphericity, which is kind of the homogeneity variance equivalent for repeated measures designs. I'm going to cover these three. Independence is kind of an easy one to cover. I'm not actually going to do any tests or anything like that, as you'll see why in a second. But let's start by importing some data, some software libraries and some data that will be useful here. So I'm going to import pandas as PD, numpy as NP. I'm going to import the stats software library from SciPy stats. I'm going to import stats models because I'll use that to fit an ANOVA. Import matplotlib because I'll do some plotting, and Seaborn as well. So hopefully that will import. Yep, successfully it has. So I'm going to import a data set that might be useful to use to illustrate some of these tests of assumptions, and it's kind of, I've got it saved as a CSV spreadsheets type of file, comma separated values spreadsheet. On my laptop it's called stress.csv. I'm going to import it as df just for data frame. I'm using the pandas read CSV method. Okay, so you can see we've got a couple of variables: employment 1, 2. It's been given numerical values, but it's kind of, these are dummy codes really for categories. New age 1, 2, 3, 4. Same sort of thing. This is a categorical variable being given a dummy code. Stress is some sort of measure of a participant's stress score, so like a scale or integer variable, and same with esteem. I don't think we need esteem. New age and stress might be the ones we'll focus on essentially. So if we look at the data types for this, employment and stress have been imported as integers. That's fine. Well, I don't think we need employment, but as it's a category, I think it'd be like 1 employed, 2 unemployed, something like that. If we need that, we're going to have to convert that to some sort of string object. Put labels on it might be more useful. But new age has been it's been identified as an object, so these are strings, even though they're actually numerical values to look at. And let's have a look at the info. So we got 465 non-null entries. So what we're going to do here is, what I'll do first of all is for new age, it's a categorical age variable where kind of 1 represents 20s, 2 represents 30s, 3 represents 40s, 4 represents 50. So it'd be useful to basically change those kind of string numbers to what they actually mean, essentially. And contrary to what I often say about just leaving the original variable in place and appending a new one, I'm going to just replace those values in the original variable on this occasion using the dot replace method. So you can see here I'm gonna take the new age variable from our data frame, use the dot replace method, and I'm passing this dictionary that says where the key value pairs, where there's a 1, replace it with 20, where there's a 2, replace it with 30s, 3, replace it with 40s, 4, replace it with 50s. So age groups, basically, people in their 20s, people in their 30s, people in their 40s, people in their 50s. And it says in place equals true is another parameter we're going to add to that. So if we now look at the header, you can see now actual string labels that are a bit more meaningful. Okay, so that's just a little bit of data wrangling, and we've got it in now I think we've got it in a format that's suitable for analysis. We can test assumptions about the data that we might seek to use for a one-way ANOVA. So we might use this data for a one-way ANOVA, and we want to test some assumptions before we do. So here we're going to focus on 2 variables. We're going to use new age as the independent variable, RIV, and that, as you know, is a categorical variable for participants, certain age bands or bins based on how old they are, 20s, 30s, 40s, 50. The DV we'll use will be the participant's stress score, so this integer stress score. I think higher scores would be more higher stress levels or something like that. Okay, so what I'll do in the remainder of this notebook is cover those 3 main assumptions, assumption tests or tests of assumptions that are necessary when considering running an ANOVA analysis. And the first one is quite easy for me to do. I'm not actually going to do any analysis or run any tests, but it's when we're talking about independence, so tests of independence. So the assumption of independence means that scores on the DV for each participant must be uncorrelated with the responses from other participants in the sample. So there's no direct statistical test to assess independence, and avoiding violation of this assumption is largely a consequence of good research design at the outset. And if it's violated, the results of the ANOVA test will be undermined, as differences between the groups of the IV may not be a consequence of the actual difference between those groups on the DV scores, because the scores on the DV for participants will be correlated in some way. Okay, so even when you have good research design, a lack of independence can still occur due to various extraneous factors and unmeasured effects. So common examples of these effects in a discipline like psychology might include things like time-ordered effect, where data is collected from different participant groups at different times, and this affects scores on the DV. So, for example, some participants may have been tested in the morning when they're more alert, some later in the day when they're more tired, and that affects kind of their scores. So data collection in group settings where participants are subject to a common experience that influences their scores, or they're able to influence each other's scores in some ways, can also lead to violations of independence. So for example, if you collect data, you get everyone together in a room and collect data, people might copy the person that sat next to them, and that's kind of, then their data isn't independent, essentially. Okay, so there are other examples, and I kind of recently, on some research that I did, was investigating if people's decisions were correlated, and it was data collected online, so I could see the times when people had participated, and if I had participants who had identical choices and decisions, and I could see that the actual date and time that they completed the study was close together, it gave me an indication that they were probably together socially or sat together when they took part, because they were just completing it maybe on their phone or something like that, so they may have influenced each other's scores. So independence, hopefully you can design it out, or you can create a design such that participant scores on the DV are not correlated with other participant scores on the DV, essentially. But there's no test, there's no specific test that you can do to assess whether data points are independent. Okay, so moving on from that, so that's the first one, essentially. Moving on from that, normality was the second assumption that we have to consider for ANOVA designs. So the assumption of normality for ANOVA is tested on the residuals for the DV. So normality can be tested using data visualization plots or certain statistical tests. On the whole, overall, visualizing and inspecting plots performs better than some sort of direct statistical test of normality. There's a lot of criticisms of those types of tests and assumptions, but a commonly used statistical test of normality is the Shapiro-Wilk test. And this test has low power for small sample sizes, and for large sample sizes it can highlight quite minor deviations from normality as being significant when they're not really an issue. So what I'll do here in the following cells is fit an ANOVA model to the stress data, so a one-way ANOVA, really simple, and then test the assumption of normality using the Shapiro-Wilk test. To do this, what I'll do is invoke the Shapiro-Wilk method from SciPy, and then I'll follow this up with a Q plot to visualize the extent to which the data deviates from normality. And it might prove interesting just to kind of like compare visualizations with actual statistical tests. So here what I've done is I've used stats models to fit an ANOVA model to the data with stress as the DV and new age as the grouping independent variable. And if I run this, so you can see here I've imported stats models, I've imported OLS from stats models, so ordinary least squares. I'm creating an object called model, which is the OLS formula specification. In parentheses, stress is a function of our categorical variable new age. Our data we're using is the DF data frame, and I've added the dot fit all in one line. And then having fitted that ordinary least squares model, and then creating an object called ANOVA table, for which we're using stats models.stats.ANOVA_ln, ANOVA linear model, and we're passing the model object to it. We're asking for type 2 sums of squares, and if I call AOV, then we get what we get is an ANOVA summary table, essentially. And it tells us we have a statistically significant ANOVA model. So we've got F brackets 4 and 460, those are our degrees of freedom. It's equal to 11.90 if we round that to 2, or 11.88 if we round that to 2 decimal places. P is much less than 0.001 in this case. You can see that's 3.412911 times e to the -09, so a very low probability indeed. So we've got a statistically significant model here. So remember, we've got 4 groups for new age, 20s, 30s, 40s and 50s, and that's telling us that at least 2 of those groups are going to differ. The means for those groups in terms of stress is going to be significantly different. Okay, so that's our model. Let's now use the Shapiro method on the object that I saved as a model here, and pass as arguments to the Shapiro method that the test will be run on the residuals. Okay, so here we're doing a Shapiro-Wilk test of normality, essentially, and we're telling Python, we're telling SciPy essentially to get the residuals from the model and run the Shapiro test on these. So I've created this new object called ShapRes, so Shapiro results, and I've set it equal to stats.Shapiro. So we're calling the Shapiro-Wilk method from stats, SciPy stats, and then what are we asking it to do a Shapiro-Wilk test on our linear model here, model.resid, the residuals from that model. And if we run that, it gives us a test statistic of 0.96 and a p-value which is very, very small. So that's I'm not going to read that out, 1.38 times e to the negative 0.9. So we'd have to move this decimal place like 9 spaces this way. So it's much lower, p-value much lower than 0.001. So the Shapiro-Wilk test from SciPy returns the value of the test statistic and the p-value, and here we can see it is statistically significant. So the null hypothesis for these tests of assumptions is that there's no difference between our data and a normal distribution. Yeah, so our data does not deviate from normal distribution significantly, is the null. The fact that the test is significant means the assumption of normality hasn't been met. And we could report the Shapiro-Wilk test like W equals 0.96, P is less than 0.001. So this is problematic for our ANOVA model analysis and suggests we may want to be cautious about drawing conclusions from the analysis about differences between our groups. So we can assess the extent of deviation from normality for the residuals in our data using data visualizations. So what we've got here is we've got a significant ANOVA. We've got a Shapiro-Wilk test telling us our data deviates from normality, and that's kind of problematic really, because we've not met the test of assumptions for conducting an ANOVA really. But if we can kind of investigate this a bit further with some plots, and as I said before, data visualizations seem to work better. So all I'm going to do here is I'm using matplotlib. I'm plotting a figure, and I'm using the stats.probplot method. Okay, and I'm plotting the model.residuals, and if I run this from plt.show as well, what we've got is what's a QQ plot or probability plot of the theoretical versus all kind of ordered values. Yeah, so the diagonal, the 45-degree diagonal there, if our points line up along that diagonal, the more they do, the more it suggests that our data is normally distributed. Okay, let's just do something else as well. So I'm gonna create a histogram as well of those residuals. So the same stuff we just used, we're going to plot those model residuals, and we can see there that's what they look like as a histogram. Okay, so the above plots highlight the value and importance of visualizing the data, I think. So the probability plot created using SciPy's stats.probplot method indicates that the extent of deviation from normality might not be as extreme as the result of the Shapiro-Wilk test indicated. So we got a kind of a significant Shapiro-Wilk test telling us it deviates from normality, and it does a bit, but it's maybe not as bad as we at first thought, because a lot of those data points sit along that diagonal line. Yeah, many of them sit along that 45-degree diagonal in the plot, indicating the observed and expected values are similar if the data is normal in distribution. So the tails of the distribution, though, they do seem to deviate somewhat from the expected value. So you can see here that these are deviating from this red line at the ends, the kind of edge behavior. So that's where the histogram comes in useful, I think. That we've played under it. It makes the picture a bit clearer, and we can see that although the residuals for the DV are starting to take on this kind of bell shape appearance, which is kind of typical of a Gaussian or normal distribution, the data does appear to be positively skewed, slightly positively skewed, and with one extremely, fairly extreme value, this one here. That's probably influencing the shape of the distribution away from normality. So given the distribution of the residuals here, an option we might consider is using a data transformation to reduce the skew, to sort of try shift it so it's more normally distributed. make it closer to a Gaussian normal distribution. Alternatively, we could kind of drop this extreme value here, I guess, removing missing values. Kind of there's some debate about whether that's a useful thing or not. It might be worth trying to transform the data first to see if that makes a difference. But what we're seeing here is, in terms of this normality assumption, using a statistical test, it's told us that data is normal, and using visualizations, it's kind of given us some indication that that's probably correct, but it might not be as a big an issue as we first thought. And in terms of using statistical tests such as Shapiro-Wilk to test the normality of your data, there are some kind of data scientists, statisticians who argue that it's not ever a good idea to do that, to rely on that. Okay, so we've done independence. There's a very little test. We just got to design things well and hope that the data are independent. We've done normality through visualizations and statistical tests. Homogeneous variance. So the final assumption I'm going to cover in this video is homogeneous variance for an ANOVA model. So this is for when we've got an independent groups design, a between subjects design. All groups in the independent variable that are being compared should have roughly equal variance, and that's the assumption of homogeneous variance, or sometimes referred to as the assumption of equality of error variance. There's various names used for it, but this means that the amount of variability around each group mean shouldn't be significantly different. So variance captures the spread of scores around the mean for each group. If the spread is significantly different between groups, then our ANOVA test may not detect differences between the groups, as greater variance for one group may just mask possible differences between the different group means. Okay, so to test for homogeneous variance, we can use both statistical methods and visualizations like we did for normality. Here, what I'll do is I'll use Levine's test and Bartlett's test as statistical tests. Both of those return a test statistic and a p-value. And again, when you get a significant p-value on those tests, it indicates the assumption has been violated and there are potential issues with the data. Levine's test is argued to be more robust when the data deviates from normality. So in the case maybe that we've got here, we've done our normality test above, we think our data deviates from normality, so a Levine's test might be a better test for homogeneity of variance. So as the residuals for the DV on the data we are using here appear to deviate slightly from normality, the Levine test might be the most appropriate. So what I'll do here is we'll do Levine's test, I'll do Bartlett's as well, and we'll use box plots to visually inspect the variability around the groups. And using the visualizations in conjunction with the statistical tests may help us get a more accurate assessment of what homogeneity of variance issues we have. So first of all, let's do Levine's test, looking at the variances between the IV groups in terms of the DV. Okay, so here what I've done is I've passed the sample data for each new age group, so 20s, 30s, each age group on the age independent variable, and we've grouped that together with the stress DV score. So I've used the SciPy stats.levine method, and here you can see in parentheses what I've done is I've passed the DV, and then in brackets after it I've passed the IV group for each one. So this first one we've got stress variable, and then in brackets afterwards we're using the new age variable that's exactly equal to 20s. So this first line here is just stress scores for 20s, the second one stress scores for 30s. Okay, so 4 groups for our Levine's test essentially. Let's run that, and what we get is a Levine's test statistic of 4.87 and a p-value of 0.002. Okay, so the Levene method's returned a test statistic and p-value. It's statistically significant, and as with previous statistical tests of assumptions that we've covered, the null hypothesis for Levene's is the variances of the different groups are roughly equal. So this indicates that the null hypothesis is unlikely to be true and that the assumptions being violated on our data, and we can't assume homogeneity or variance. So the Bartlett test is similar, and we can use the SciPy stats.bartlett method for this. So you can see that I've pretty much, apart from the word Bartlett instead of Levene's, it's kind of, you can see it's pretty much the same syntax where we're extracting the stress scores by each age group individually, and you see we get a test statistic of 25.78 and again a statistically significant result. So both of these tests are sort of indicating that the assumption of equal variances between the groups has been violated. And here what we can see is Bartlett's returned a test statistic of the test statistic we report for Bartlett's apparently is omega, capital omega W, and that's equal to 25.78. P is less than 0.001 in this case. So we're pretty sure we can't assume equal variances for this particular data set. And with these tests, with these different tests, if we find we weren't able to meet these assumptions, we'd have to find some way. We'd have to do a more robust test. So we'd have to do maybe a Welch's ANOVA or something like that. For a one-way ANOVA, that would be an option. But what we can do also, though, in addition to these statistical tests, is use a box plot to visualize the variance around the groups. That'll give us a bit more of an indication of kind of what this all looks like. So I'm going to use matplotlib to create a box plot. So you can see here I've kind of created some axes, I've created a figure, I've created some axes. I'm telling it to use the data to use is this, which was the different groups, and I'm saying ax.boxplot, okay, using data, which is this object here, essentially, that I've just created above, and the labels 20s, 30s, 40s, 50s. Show means equals true, so it'll give us a nice kind of indication of where the means are on this data set. All right, so let's have a look at that. That's what it looks like. So 20s, 30s, 40s, and 50s. So you can see that with kind of, if you include the outliers as well, we've got some across these different groups. It's given us some quite useful contextual information to understand kind of what why we got these significant Levene's and Bartlett's tests. So we can see the group means that they differ based on the yellow line. So we see 20s, stress in the 20s age groups higher than the other three. However, the variability about each group mean differs significantly as well. So the 50s age group, this one here, has the narrowest spread of scores. So if we look at the interquartile range there, the whiskers beyond the interquartile range, it's that'd be 1.5 times the interquartile range. That's quite narrow for the 50s, but if we look at that in contrast to the 20s age group, that has a much wider range of scores. There you can see that cover all. Not quite, but if we had these outliers for that particular age group as well, like boom up here, it covers almost the whole range of values on the stress scale. Okay, so what that indicates, though, even if if group means were different, this kind of large spread of scores based on these whiskers here in the 20s age group will overlap significantly, and the ANOVA may produce kind of erroneous results. So even if for this one maybe the stress score was like the mean was up here somewhere, you'd still get overlap, considerable overlap between the groups. All right, so when we're working with this particular data set, you may want to look at any scores that are outliers and remove them, see if this makes a significant difference to the group variances if it makes them more equal. So maybe if we remove these outliers here, it would probably reduce the spread of scores on this variable considerably. Maybe with the others as well, it might be worth doing that. So what I've done here as well, though, underneath is just to sort of indicate how big the differences are. I've used the NumPy .var method to obtain the variances for the 20s age group and the 50s age group, and we can see that these two values are actually quite different. So you can see there the variance for the 20s is 26,733, and for the 50s it's 11,252, so it's like less than half the size in terms of variance. So obviously that's a kind of a strong indication that we don't have equal variances, just eyeballing those two values. Okay, so that's all I'm going to cover in this particular video. Just to summarize what I've gone through here, so there are three main assumptions that have to be met when we conduct an ANOVA test. Remember, it's a parametric statistical test, it's a frequentist statistical test, a null hypothesis test. It's best used for experimental designs. Independence is one of them. There are no direct tests for this, and it needs to be considered in the design stage of an experiment or a study. Normality can be assessed using data visualization and statistical tests. In ANOVA, normality is tested on the residuals of the DV. The Shapiro-Wilk test can be used to do that. Useful data visualizations for normality include QQ plots or probability plots, histograms to visualize the distribution of a variable. Homogeneity variance is the assumption that variances around the group means being compared are roughly equal, and this can be assessed using data visualization and statistical tests. So the Levine's test and Bartlett test are both tests of equal variances. Levine's test is argued to be preferable when the assumption of normality has been violated. We can use box plots to visualize the spread of scores for each group as kind of to follow up or to investigate further what exactly is going on. On the whole, data visualizations tend to perform better than statistical tests of assumptions. Statistical tests of assumptions have several weaknesses in that they may be underpowered when sample sizes are small, or may highlight small deviations as significant in larger sample sizes. And there are some statisticians and data scientists who suggest you should never do these kind of, you shouldn't trust the results of these types of tests of assumptions. And if there is an issue, you're probably better off using some sort of robust analysis. Okay, that's all I'm going to cover. That is the end of the videos I'm going to record for now on ANOVA. I'm a bit bored of ANOVA. We've done too much of it recently. So the next video and the few after that, I'm going to move on to regression. So we'll look at some assumptions and diagnostics for regression. Then we'll look at simple linear regression and move on to multiple regression over the next few videos. I hope this was helpful. Just some things to consider when you are running an ANOVA test. Okay, thank you for listening.